Esto es la red LAFMAT, la red latinoamericana en física de materia condensada y ciencias materiales, conformada por universidades de distintos países latinoamericanos. Como todos los sábados, organizamos una conferencia en línea. El día de hoy tenemos a nuestra invitada, profesora Jiwon Seo. Ella es coreana de la Universidad de Yonsei. Es una gran amiga mía. Estudiamos juntos el PhD en física en el laboratorio Cavendish de la Universidad de Cambridge hace más de una década, más de 15 años. Luego ella viajó al Nanyang, a Singapur, para trabajar en el Nanyang Technological University en Singapur. Luego regresó a Corea del Sur, donde actualmente es profesora en la Universidad de Corea del Sur, en la Universidad de Yonsei University. Su especialidad es Material Science and Acoustic Nanomaterials, Metamaterials, y también Interlayers, estructuras, heteroestructuras, filmes delgados, propiedades físicas de las multiestructuras, diferentes capas. Bien, ella habla inglés y voy a presentarla también en inglés. Good morning, everybody. This is the LAFMAT network, the Latin American Network of Matter Condensed Physics and Material Science. Today, we have our invited speaker is Professor Jiwon Seo from Yonsei University in Korea. Jiwon Seo studied a PhD in physics in the Cavendish Laboratory in the University of Cambridge. Then she moved to Singapore, to Nanyang Technological University in Singapore. After that, she went back to Korea, South Korea, and now she is a professor at Yonsei University. Her expertise is about material science and acoustic metamaterials, interlayers, and multi-layers thin films. Well, welcome, Jiwon Seo, and you can start your talk now. You can share your screen and start your talk.
Okay, thank you for introducing me. Then, okay. Mhm. Sorry.
Yeah, we can see your screen now.
Okay.
Maybe you can full screen, maybe.
Okay. Oh, okay.
Yeah, but you can maybe share
Yep.
full screen.
Yep.
That's good. That is good. Okay, go ahead.
Okay. Thank you for introducing me and then inviting me here. I'm Korean, South Korean, but I'm quite happy to be here in Latin American society. Especially Luis is my old and good friend, and he's nice man. Okay. Today I'm going to introduce about looking for. Sorry, this I cannot see the title. Okay. Today I'm going to introduce about looking for multifunctional devices using interfacial effects in heterostructures. If you want to make a new material you need, then maybe you can compose the material using the periodic table. You can choose some atoms and then mix together and then compose some new materials. But we can make a new material just using interface. In the period table, you can see some transmetals like this. In transmetal oxide, this has a very interesting behavior. Transmetal oxides competing interaction among the spin, charge, and orbital degree of freedom. Especially the interface between the transmetal oxide offset the balance of the competing energies and then leading to significant deviations from the bulk characteristics. So we can generate some emergent properties at interface, which is not same as the bulk properties. Okay, it's a very old story. Chakalasian first published his paper in Science. He used some materials, and then at the interface, they show some orbital reorientations. Also, Otomo and Huang published this some lectures using these materials. They use the strut titanium oxide and lanthanum aluminum oxide. Both of them are non-magnetic insulators. Both of them are non-magnetic and insulator. Then they put together. Then what happened? Because of the interface, they show some high mobility, electron gas at interface, and then some ferromagnetism, and then superconducting. Yeah, it's so amazing because both of them are non-magnetic insulator, but they show high mobility electron gas and ferromagnetic superconducting. So many researchers try to use some field effect devices and then some field effect room temperature ferromagnetism using these materials just to use the interface. So researchers wonders why it happened. There are many reasons. Charge transfers due to the polar discontinuity, potential differences, and oxygen vacancies, and low dimensionality because of the films, and then reorientation of spins and orbitals at interface. Or sometimes the structures change at the interface, and there are many reasons. Okay, today I show you two examples. One is manganite using some lanthanum, strontium, neodymium. Then we make a superlattice. And the other one is strontium oxide, and then calcium mangan oxide, strontium mangan oxide. It's a tri-layer, just to use the three layers. It's a manganite is sandwiched by two strontium oxide. Okay, let's see what happened at this superlattice. Okay, this superlattice is composed of three different kind of layers: lanthanum mangan oxide, strontium mangan oxide, neodymium mangan oxide, and then we repeat it again and again to make a superlattice. All layers are antiferromagnetic insulators. Antiferromagnetic insulators. But if we put together, then at interface, something happened. Okay, this page show the quality of the films. The roughness is less than 1 angstrom. The surface roughness is less than 1 angstrom. Then it's a read result. They show one layer and one layer text. Okay, first, this antiferromagnetic insulator superlattice show ferromagnetism. This is magnetic hysteresis. Depending on the thickness of each layer, they show different shape of hysteresis. Okay, if you see the circle, then they say 22. It means each layer has a 22 unit cell thickness. Then we keep the total thickness is around 15 nanometers. Okay, let's see this one. They shows very clear the hysteresis, magnetic hysteresis. If we make a 5 unit cell thickness of each layer, then it shows the largest the hysteresis and magnetization. Then the thickness is thicker, then is the hysteresis become narrow, and the magnetization also become lower. So this graph show the depending on the period, the cohesive field is going up and going down like this. So in this kinds of material show some critical thickness. In the case around 5 unit cell, they show the peak of magnetization and others as well. So we can see the critical thickness is around 5 unit cell. Someone maybe think it's not interface effect. Maybe you made some mixture at the interface, so that mixture can make the ferromagnetism. So I did some neutron reflectivity measurement. This data shows at interface the magnetic signal is very high, like this. Okay. 300 Kelvin is over the Curie temperature, and 10 Kelvin is below the Curie temperature. At 300 Kelvin there is no peaks, but below the Curie temperature you can see some peaks. This peak is due to the magnetic properties at interface. It should show very clearly like this. So from this data, we said this ferromagnetism is from the interface. Okay, then let's see. We said at interface there is a ferromagnetism, and some reason far from the interface they have antiferromagnetism. If they are nearby each other, then what happens? Like this, there is the spin has some frustrations. So ferromagnetic, and at interface, the spin feels frustration. So they gave rise to some spin glasses. We found spin glasses behavior as well. See this case, we turn on the magnetic field and turn off. Then we measure the magnetization as a function of the times. Even it's around 1 hour later, but the magnetization is slowly decreasing. Also, we turn on the magnetic field, then the magnetization is going up until 2 hours. So the magnetic is very moving slowly. This behavior is a very typical characterization of spin glasses. In electrically, we found some ferroelectric behavior as well. This is polarization data. This one also shows hysteresis, like magnetic hysteresis. As you will remember, this material is non-magnetic, antiferromagnetic, and insulators. Then they show some ferroelectric behavior as well. Professor Dokura suggests some structures. In his suggestion, he said if the material is like a bicolor, he said it's a bicolor. It's a 2 layer and repeat two layers. Then at the interface, there the polarization is present, and then the polarization is cancelled because this interface polarization and that interface polarization are same and opposite direction. The amplitude is the same, but the direction is opposite, so they are cancelled. So there is no electrical ferroelectricity. But if we break the symmetry, then we can find there's some the polarization like this. We found this, the butterfly-like shapes in capacitance as well. This is a kind of behavior of ferroelectricities. Then this polarization is depending on the period. It's the 2 unit cell thickness, 20 unit cell thickness, and then 5 unit cell thickness. Yeah, this means 5 unit cell thickness of each layer and 8 times repetitions. This case is 2 unit cell thickness of each layer and 21 times repetition. Depending on the period, the polarization show differently. The transition temperature is 20 Kelvin, sometimes 40 Kelvin like this. In case of 5 thickness of unit cell is 20 Kelvin transition temperature, and the 22 case is around 40 Kelvin transition temperatures. This. We also measured some dielectric constant like this. Then it shows the frequency dependence. As increasing the frequencies, then the peak is shifting toward the higher temperatures. And then low temperature, there's no frequency dependence. This temperature is almost the same as the transition temperature of each material, thin films. In 22 case is around 40 Kelvin or something around that, and then 5 unicells is lower than 20 Kelvin like this. The frequency dependence say the material has some time dependence, like spin glasses. This one also has some time dependence. Yeah, so we call it ferroelectric relaxer. Until now, we see ferroelectric, ferromagnetic, spin relaxer, and ferroelectric relaxer in these materials. It's quite wonderful because we used just anti-ferromagnetic insulator, but they show quite emergent properties in these materials. Then we try to find more interesting things in these materials because they shows ferroelectric, also ferromagnetic. So I'm thinking there is some multiferroics. So the magnetic and electric can correlated each other. So we can tune some properties by others. Okay, this is polarization result. We applied magnetic field around 6 Tesla like this. Then the polarization, the electrical polarization changed. It's going up almost twice like this. Yeah, it's some electrical polarization, but it is interacting with magnetic field. Also, 6 Tesla, then the curves move to the lower temperature, like this. This data show the ferroelectricity or relaxer is interested in with the magnetic field. So electrical property and magnetic property are correlated each other. This is some pump proof reflectivity measurement as a function of time. We hit a laser on the sample, then the oscillation is showing up like this. Yeah. We found the intensity of this oscillation has like this. This one also has some critical thickness around the 5 unit cell. The amplitude of this oscillation is big compared to others. It's similar with the magnetic hysteresis. This oscillation also responds to the magnetic field. Below the Curie temperature, in magnetic field or without magnetic field, it's almost similar. But below the Curie temperature, in magnetic field is different from the without magnetic field. So this phonon oscillation also related to the magnetic field. It's interesting. We found some orbital structure is correlated with magnetic field as well. This is the result of XLD. Maybe someone is familiar with this tool or others is not. XLD is some tool to see orbital structure in films. We use X-ray with polarization. So depending on the polarization direction, then the amplitude of interaction is some different. We used different kind of polarization. Then we get the differences between two different polarization of X-rays. From this one, we can know the orbital structures. Yeah. In that case, one unit cell thickness film, then they show quite differences between in and without magnetic field. The blue one is measured in without magnetic field, and pink one is measured in 0.7 Tesla magnetic field. If the layer is 1 unit cell thickness, the orbital structure is changed depending on the magnetic field. But the thicker one case, the orbital structure is almost same. Okay, we calculated and then analysis the result. Without magnetic field, this orbital is along the z direction. This orbital has 40% of occupation, and then in plane orbital is a 60% occupation. But if we apply the magnetic field around 0.7 Tesla, then in plane occupation is 45%, and out of plane orbital is 55%. The percentage is changed because of magnetic field. So orbital can be changed by a magnetic field. This result showed that one. Okay, my collaborator calculated these materials using first principle calculations. Depending on the polarizations, they show some there is spin polarized, the metallic behavior. There is a density of a state. Then change the direction of polarization. This is closed. So this is not the metallic, and there is no spin polarization. If we change the polarization direction, then instead of lanthanum oxide, instead of it, the neodymium oxide show metallic and spin polarized density of state like this. So these results show, depending on the polarization, the magnetic also can change it. The layer is changed. The collaborator calculated the distance of atoms like this. The distance of atom is very close to the behavior of magnetic properties, magnetization like this. So it means the distance of atoms is closely related to the magnetizations. Okay, until now we show the emergent properties at interface. Also, this zone can be controlled by light or magnetic field, sometimes the electric field. The properties are very close to each other, so you can tune some properties by other field. So we can design some multifunctional materials using interface. Okay, this is summary for my first materials. We found ferroelectric, ferromagnetic, and ferroelectron relaxer and frustrated magnetism as well. We see some magneto-electric, magneto-elastic, and magneto-optical coupling and magneto-orbital as well. So these kinds of material can be used for multifunctional devices. Okay, this is my second material. This material is using strontium oxide. This material is very well known. Is well known to be used some spintronics materials. This is ferromagnetic materials. Between two ferromagnetic materials, we use antiferromagnetic manganite. We use these three kinds of manganite. All of them are antiferromagnet and insulator, but they have a different type of valence state. 4 plus, 3 plus, and half and half, like this. Also, we change the substrate like this. We use two substrate. Strontium titanium oxide has a larger lattice parameters than lanthanum aluminum oxide. This is a spin structure of each layers. Ferromagnetic has spins up, and then antiferromagnetic is between the spins. Okay, this is a TEM image. Okay, this one also show the structure diffraction, and then from this one we know lanthanum aluminum oxide gave strong compressive strain. Strontium titanium oxide also gave us compressive strain, but it's okay. It's almost one, but their case is much stronger. My research is motivated by this result. In this result, they show two quest field like this. One is here, the other one is here. They said this quest field is because of the pinning of magnetic field spins at interface. This one is from the strontium oxide, the ferromagnetic material, but at interface, this one is pinned, so it's become wider than before. So I'm interested in the interfacial the spin. Okay. Then I used X-ray magnetic circular dichroism. This is a tool to see some magnetic properties at some buried layers in the buried layers like this. The manganite is below the strontium oxide. If you use squid, then we just see the total magnetization. But if we tune the energy of X-ray, then we can see only the layer of manganite. In the case we tune the energy around 640, is the absorption edge of mangan. So we see only the profiles of manganite. From this one, we see the insulating and antiferromagnetic. This manganite has upside magnetization in the case of LAO substrate, but strontium titanium oxide substrate case, the spin direction is opposite compared to the before. Yeah, from this data, we think about something like this. This is a piezoelectric substrate. So if we can apply some electric field, then we can change the strain. Then maybe we can change the direction of the spins. Yeah. So we can get some difference of resistivity. So we can make a device of spintronics like this using some electric field. But we did not make up this device because it is hard to find some substrate which is matching with the other layers. Yeah. And then we see some interesting things using the measurement of resistivity in magnetic field. This case, at very low temperature, below the 4 Kelvin like this, the resistivity is going up, like Kondo effect. But if we apply the magnetic field, then this behavior is going down, like the red one. And also, depending on the current, the behavior is changing very differently. Then interesting is we've checked the hysteresis of magnetic hysteresis, but this film is very small, so we use the resistance measurement. This is magnetic hysteresis, then this is resistivity, then the butterfly shape, say this peak is correspond to the cohesive field. Yeah. In the case at 10 Kelvin, there is no dependence on the current amplitude of current, but very low Kelvin at very low temperature is at 1.7 Kelvin. The resistance depends on current. It's like this. Also, the quest field here is changed by the current. In this graph show the quest field is changing by the current. Just we applied 2 milliampere, but it's a change around 20% of quest field. It means we can control the quest field using current. Yeah, it's a kind of a spintronics device. It's like a spintronics device. So it's a second summary. So we can control the magnetization using current or electrical field. So this also is multifunctional materials. Yeah, until now, we focus on some interfacial effect. Then why interface is important and useful? First, they show some emergent properties not shown in the phase diagram. Yeah. In these phase diagrams, we cannot find any ferroelectricity, but we can generate the ferroelectricity, the electrical lexer, and then ferromagnetics, also and lexer as well, spin glasses. Also, the interface, the property interface is metastable. It's not like a bulk, it's metastable. So if we give a small external perturbation, then it gives rise to large effects. Also, we can tailor some property we need just by changing some thickness or period. Also, one kind of external stimulation, then we can tune several kinds of degree of freedom. So if we give some magnetic field, then we can change the lattice parameters or phonons or orbitals or some electrical polarization. So we can change many properties at one time. Okay, it's my collaborators. Wilfried Prilliar is this lab in France, and then Seung Park is a Korean-based science institute. He helped to measure the very low temperature resistivity. In my lab, I can measure the resistivity until 5 Kelvin in 1 Tesla, but he helped me to measure the resistivity on up to the 1.7 Kelvin, and then magnetic field is up to the 9 Tesla. And Christopher Vanarkopoulos is my supervisor of my PhD degree. Now he moved to Nanyang Technology University from the Cambridge. And then now my students is like this. Okay. This is my new topics. Now I'm doing some research regarding acoustic materials and then other some spintronic materials. Is acoustic material also to find some materials, functional materials. So in nature, we only found positive density and bulk modulus materials, but we can design negative materials. If there is some materials like effective mass density is 0, then it's moving like this. Also, if effective density is very high, then it's not moving. Also, if the sounds become very slow, then the time resolution become good. So I'm doing something like this. So I make some heavy material to block the sounds, and then light material to get some energy harvest. So it's okay. I made a very slow sound. Its phase velocity is 26 meter per second. Okay, you may imagine the sounds of the speed of sounds is 340 meter per second, but I can make a very slow sounds. It's like this, 26 or something. Some cases, 16 meter per second. So I used this structure to get high resolution of time resolution, high time resolution. If there is a crack, we put some pulse like this, and then it's coming back. Then the signal, two signal is overlapped, so we cannot get the distance of this one. But if the sound is slower than that one, then we can see the separation of the signal. From this one, you can get the distance of this point. Okay, thank you for attention. Thank you.
Thank you very much, Jiwon Seo. Now is the time for a question from the panelists. But first, yes, you didn't write my name on the collaborators. We are collaborating recently.
Yeah. Sorry.
Don't worry. Now we are going to move to the panelists, to their question. First of all, Professor Stuart Holmes from the University College London and University Cambridge. Stuart.
Thank you, Jiwon, for the nice talk. You gave a lot of information there and lots of publications. I have some technical questions.
Okay.
I know with these materials that the preparation of the substrate, the properties of the interface can be very dependent on how the surface terminated. If the oxygen bonds are in one particular way, you can get an electron gas or a hole gas at the interface. I think you've mainly talked about electron gases. Do you ever see a situation where you would get a hole gas? Probably have to use the Hall effect to determine. But do you ever see p-type behavior in your interfaces?
Oh, thank you for your question. I didn't measure the type of carriers. Okay, what I said is the suggestion from others. Actually, I didn't measure the exact type of the carriers. Sorry.
That's okay. I think the default in, say, in LAO, STO, if you make that interface, you get an electron gas.
Yeah.
Because of the way the bonding can happen at the interface, can also stabilize a hole gas.
Yeah.
I think the default is an electron gas. Okay, I have one or two other questions. I think also you didn't mention doping. I think oxygen vacancies act as doping. Do you have problems with these systems that they're overdoped? You have too many electrons in the system?
Yeah, so I made many interfaces.
Yeah.
Yeah, if there is oxygens, then maybe the whole material, whole film shows similar behaviors. But depending on the period and depending on the thickness, the behavior is totally different from each other.
I have one more question, which was on the second part of your talk.
Okay.
You were applying the magnetic field perpendicular to the surface.
Yes.
Did you ever study the effect of an in-plane magnetic field on the system?
Yeah. I did, but the signal is smaller than the out of plane. I didn't show it here, but
Yeah.
okay, I didn't show here.
I mean, it looks like an anisotropic magnetoresistance.
Yeah,
here.
you're right. Yeah. The signal is very big in case of out of plane, but
Yeah.
in plane case is small, much smaller. So we can find some magnetoresistance in case of in plane magnetic field.
I mean, it looks, your data here, it looks like it's about 40%. The MR would be, say, 40%.
Quite big. Yeah.
Quite very big, very big.
Yeah.
Such
very
a small
big.
field. I mean, you
Yeah.
might find in these materials that your AMR is maybe 0.5% or something like that. It should be still there. Very interesting talk. Thank you again. I'll stop there. Let other people ask questions. Thank you for your interesting talk.
Thank you for your question.
Thank you very much, Professor Stuart Holme from the University College London, University Cambridge. Well, now one question, Jiwon, about the thickness. The thickness are monolayers or usually the layers of the manganese, and also the thickness of the interlayers itself. They're usually less than 1 nanometer. Are monolayers as well, as I suppose, right? Less than 1 nanometer or so, the interlayers, and also the substrates and the layers. What are the thickness roughly that you work it? Of course, that it changes with the thickness. It will change, of course, but when you work it.
Okay, the 1 unit cell is around 4 angstrom. Okay. And the interface is quite sharp.
Yes, with the AFM you check, right? Yeah.
Yeah.
Okay, nice. Thank you. Now we are going to move to Chile. Okay. In Chile, we have in the University of San Sebastián in Puerto Montt in the south of Chile with Professor what is it? Felipe Mundaca is there. Felipe.
Hello, Professor. Thanks for your lecture. Very nice. Please, can you project the density of state result by ab initio?
This one?
Yeah, this. Yes, this. My question is how you calculate this density of state. For example, I don't understand the system model. You have a different density of state, but I don't know what represent of the system. I don't know if you can explain that.
Okay, as I said, is my collaborator calculated, and then okay, this one, the upside, it means the spin upside, and down means the down is a spin down state. Is it you wanted what you wanted? And then if there is something in case it means there is a gap because there is no state, but there is a something opened. There is something, so it means there is a state, and then the spin is down state. So it means the spin is polarized. I don't know. It is what you wanted to know.
Sorry, right? I lost my connection. Sorry. Yeah, I lost my connection. But my other question is for example, you have different metal oxide, and when we simulate the density of state, when we use the for example interlayer material, we use one crystallographic plane.
I see.
You use the most stable crystallographic plane or
Recording in progress. ¿Le puede extender la pregunta?
Recording in progress.
This one is right?
Yeah,
Yes.
go ahead.
Okay, this one is for, we use circular polarized X-ray. If we use linear polarized, then we see the orbital structure. In that case, we use a circular dichroism. Then the circular dichroism is response to the magnetism of the materials. And if we tune the energy of X-ray, tunes to some absorption edge of some atom, then we just see the property of magnetism, the magnetism of the atom we tuned. See, this is energy and this is intensity. This is original data. We use the two different type of circular magnetic dichroism. The clockwise or anti-clockwise show different absorption spectroscopy like this. Then we get the difference between them like this. So we see the point here is a different. It tells the difference between the circular dichroism is around 15%. That case is 60%. This is 1.5% like this. It means that one has much bigger magnetization magnetization compared to others, like this. Also, this graph gave us some information of direction of spins. If that one is like this, it means it's that direction. If it's opposite like this, then the spin direction is the opposite to the left side. So this analysis gave us some information of spin direction and then the strength of the magnetization in some specific layers. So we can choose the layer we want to see by tune the energy of X-ray. Okay. Yeah.
Okay, Blanca, ¿alguna otra pregunta?
Muchas gracias, es fascinante el tema de ella. Gracias, se lo dice por favor.
Okay, she said gracias, which means thank you.
Yeah, I know that. Gracias.
Okay, well, now let's move to Mexico, to Monterrey in Mexico, in the CIMAP Institute, Materials Institute of Advanced Material Institute, CIMAP, in Mexico, with Margarita Sanchez. Professor Margarita Sanchez, are you there?
Yes, I'm here. Can you hear me?
Yes, go ahead.
Hi, good morning, and thank you very much for a very interesting presentation, very fascinating. I didn't know about these effects. It's not my topic at all. And I was wondering, all the systems that you show, of course, they are very thin and flat interfaces or multi-layers. And as you mentioned at the end, you can tailor-make the properties by changing thickness and period, and of course the nature of the material. Somebody mentioned maybe doping and so on. And I was wondering first if it would be possible. I don't know which synthesis method was used for the preparation of these, or the fabrication of these materials, of these multi-layers. But I was wondering if it would be possible to introduce some nanostructuring, like if you grow the multi-layers onto a template with a certain pattern, nano pattern or micro pattern, and first if it will be possible with the techniques of with the deposition techniques, and second, if such structuring will have an effect on the properties that you mentioned, that maybe such structuring might magnify the effects. Thank you.
Thank you. Yeah. First one, okay. Yeah, we can make some nanostructure. Yeah. Okay. In Korea, the Samsung has a very wonderful technique to make nanostructures. To make a nanostructure, we use the excimer, the lasers. So we can use the nanostructure, but already the interface is nanostructure or angstrom structures. It gives.
I mean, instead of having a flat, having some pattern.
Yeah. Maybe that can give us some interesting behaviors, but I didn't try that experiment.
I believe at the end when you introduced that you are interested in metamaterials, I thought maybe that's the direction.
Yeah. Yeah, it's a good point. Yeah. But now I'm doing some acoustic materials. So, yeah, if we make some patterns, maybe it will give us some very interesting informations. For example, the substrate has some nanoscale or angstrom scale step and terrace, like this. Depending on these step and terrace structures, the property of the film is changing. Yeah. So as you suggested, the structure is very important as well. Also, depending on the direction, is if step and terrace is like this direction and that direction has a different behavior of resistivity. So, yeah, the structure is important, as you suggested. Okay.
Okay, thank you. Yeah, maybe something to work in the future. Thank you very much.
Maybe, yeah. I cannot understand your second questions. Can you say again?
No, the second question was if it's related. It's just if the property you already answered. If the
Okay, thank you.
properties will be maybe magnified or different in as a function.
Differently, yeah. I cannot guarantee the magnify, but yeah, it's different. Yeah, surely it's different.
Thank you very much.
Thank you.
Okay, thank you, Professor Margarita Sanchez from Mexico, Monterrey, Mexico. Well, now let's move to the last country, Colombia, which are connected today, Colombia, with Ximena Velázquez. You have questions or questions from the public, Ximena?
Good morning. Good morning, Professor. No, I don't have any question. Well, that was an interesting talk. Thank you for that. Here in my network, no, we don't have questions from our university. Thank you for your talk.
Thank you.
Thank you, Ximena. There is one question from online, which is from Pierre Giovanni Mani Gonzalez. Is apparently from Sinvestab, Mexico. He left his questions. Says, nice talk. Thank you for showing your research. Did you analyze the composition of the interface of your multilayer by XPS?
Yeah. Which property do you wonder?
It says, have you analyzed the compositional interface effects of these multifunctional magnetic properties by XPS? Basically, it's asking if you study by XPS. But you know, XPS is a surface technique.
Yeah.
It is a multilayer, but that is his
Yeah,
question.
yeah. Okay, I tried XPS to see the density of state. Because this material shows metallic behavior, even though each layer is insulating. Just to see this one, I performed the XPS. So I found the density of state near the Fermi surface. So I confirmed that this one is really metallic. But XPS is not good for see the depth reserved properties. It's not depth reserved. It's just for surface sensitive techniques. So yeah.
Okay, nice. Oh, one final question, because there is no more question apparently. You mentioned about the optical properties, the optical band gap, or maybe the UVs, or any measurement that you have checked. The optical properties itself. Maybe the band gap changes there because of the interlayers or something. Maybe you have analyzed them with that technique.
No, I didn't.
Okay.
Yeah. Just using the photo emission, I see the density of state, but I didn't do under the magnetic field or other stimulations.
Okay, excellent. Okay. Well, is anybody here on the panel have any question, any further question, or the public? Anybody? ¿Alguien más tiene una pregunta de su público? Okay, nobody. Well, maybe you can stop sharing your screen, Jiwon.
Okay.
And maybe you word to say goodbye, maybe.